colours. 1HG1, the lights are on, just up the front there, we're going to stuck out for that. Don't know what's seen on this group, but 1HG1. Does anyone else need any more handouts? The gentleman who just came in next to Keith there, just arrived, so it's like a handout there. Anyone else who needs or might? Yep, absolutely. Pass one down there, guys. Yeah, I think. Anyone else? Yep, cool. I'll come down. Right, so I think we're ready to rock and roll. Hi guys, thanks very much for coming up. First night of the year for us, and I thought we'd start with covering some galaxies. So first of all, just some general introduction of what we're doing here, because I spotted a lot of new faces here, so new members, that's really great. And these talks are all about appealing to everyone. So there's no need to worry about, oh gosh, I don't know much. It's talks are designed for everyone to take at least 1 or 2 points away home tonight. Try to provide value. I know the seats aren't the most comfortable, but you've bothered to come out of your homes on a Monday night, so I try to make it such that when you go home, you think, I'm glad I came out for the night. So it will spill over a little bit more than the hour or so, but that's why I want to really give you something to take home and be happy with. These talks are all about sharing the learning. If there's anyone else out here who is doing some learning, some study, astronomy related, and you want to share it, because I can strongly encourage it is a good thing to share what you're learning. A, it's fun, but B, it's a great way of learning yourself. If you're just interested in a 5-minute or a 10-minute or a 20-minute or a 30-minute or a 60-minute slot, come and see me afterwards, or send me an email if you like, and say, hey, I'd be interested at some time doing a presentation. So I think that's important, just to keep people sharing what they're learning, and I'm sure a lot of you are learning some stuff out there, and it's a great way to learn and just actually share what you have learned. So I encourage you there. The other point is, why galaxies? We've done, over the last couple of years, we've had talks on the solar systems, we've had talks on various star types. Peter Feldhofer's done a marvellous job in covering a lot of aspects of cosmology. I thought, 2017, what should we do? Aha! What's the elephant in the room? Galaxies! So we're talking all about galaxies this year. So that's what that's all about. Let's see if I can work this. Here we go. So there's going to be six sessions this year on galaxies. Tonight's a general introduction to galaxies and how we classify them. Then there's 2 talks on the Milky Way galaxy. It's very, very important. It's fascinating. Hey, and it's home. We're going to then talk about the galaxies within the local group. They're all our neighbours. Then there'll be a talk on the current theories on how galaxies form and evolve. And then the wonderful world of galactic centres. We're going to have a whole talk on those, on supermassive black holes, and when those things, babies, start chewing and spewing, they become AGNs, active galactic nuclei. So that's a whole wonderful field as well. So that's what we're going to be covering for the year. The format of each talk, first of all, will be a 30 to 40 minute talk about one of those topics. We're going to try and cover. It's important to recognise historical figures. So we're going to have a little chat about relevant history of astronomy, learning some principles of general astronomy, and along with the principles of galaxy astronomy. And I think it's important always to talk about the tools of modern astronomy. Hey, the tools that they use to get this information is important. Followed by, I thought this is something new this year, I've got some pre-recorded lectures from professors in the United States on astronomy, very, very good, and I've chosen a 30-minute one for each session that quite nicely reinforces and expands on some of the comments and just breaks it up to make it more interesting for you guys. And then there's always time, general discussion and any questions. Probably at the end of my talk we can have a little bit of any questions and general discussion, and we'll move on to the movie and do further with that. Okay, so let's move on to tonight's session. There's some of the figures, key historical figures we're going to be talking about tonight. We're going to talk about variable stars. That's an important part of astronomy, general astronomy, to study galaxies. Then we'll talk about how to classify galaxies, and that goes hand in hand, it flows on nicely to a thing called Hubble's law, because of Edwin Hubble we'll be talking about. And then for tools, we'll talk a little bit about space telescopes and the importance of multi-wave wavelength observations. galaxies, they creep into society and our everyday living and so on. Everyone knows that poster a long time ago in a galaxy far away. Also sneaks into our humour. I like that one. Okay, so first of all, let's form a definition of galaxies. Gravitationally bound system. That's important. Gravity is probably the key fundamental force of nature that holds galaxies together and other large structures. Your solar system, galaxies, galaxy clusters. Interesting enough, it does not hold superclusters together. That's something completely different. That's controlled by the Hubble flow, the expansion of the universe, helps to sculpture and mold superclusters. But certainly your solar systems, your galaxies and your galaxy clusters are structurally held together by gravity. That's important. We'd be getting nowhere without that. Dark matter? Dark matter is important. What is dark matter? Everyone talks about, what's dark matter? Dark matter is very elusive. It's some sort of exotic particle. They haven't been able to identify it yet, but they're certainly looking for it. Why is it so elusive? It's because it does not emit or absorb any electromagnetic radiation, i.e. light. So very, very hard to detect, but it interacts with gravity, and that's what makes us able to detect it. And the best analogy, trying to get your head around that one, think of yourself in a room by a window on a windy day outside. You can't see wind, but you see the trees all blowing over. You see someone's umbrella turning inside out. You see a rubbish bin rolling down the road. You know it's there, you just can't see it. And it's the same principle with this. Importantly enough, dark matter makes up most of the matter in galaxies. In particular for the Milky Way, the stars that we're looking at, the stars and the dust, make up 10% of the gas, 10% of the mass of the Milky Way. 90% of it is dark matter. So that's real important too. And of course stars, different various star types which we've learned about, we'll continue to talk about. Stellar remnants, that's black holes, neutron stars, white dwarfs. Interstellar gas and dust are supposed to make up all your gas and dust between stars, but also your nebula and so on. So another way of looking at galaxies is that if solar systems and stars are homes, then galaxies are cities. They can be small cities, the size of Ekatahuna, or they can be large cities the size of New York City. To give you an idea of numbers, it's estimated there's probably about 200 billion stars in the Milky Way galaxy. Check that out, 200 billion stars in the Milky Way galaxy. And they estimate in the observable universe that there's at least 100 billion galaxies in the observable universe. Total all that up, there are more stars in the observable universe than there are grains of sand in the entire planet Earth. Whoa, check that out, amazing. Now, it's not always, all these facts and figures haven't always been sown. So let's back up the bus and let's talk about some history. So we're going to talk about these guys here. There's six figures that I've picked out. Let's start with Galileo. Galileo was the first guy, of course, he was the first, the telescope just got invented just before he picked it up. He was the first guy to actually observe the heavens with it. And up till then, the Milky Way, I've got a picture of what the Milky Way looks like. And this incidentally from Greg Stevens, one of our own members, took this picture here, which he won quite a significant prize with Greg, I think an award down in Franklin. So this is Greg's photo here, full credit to Greg, it's down at Fiji Lighthouse. So over the years, prior to Galileo, they just looked at that and it just looked a nice warm fuzzy white strip, so they called it the Milky Way. Galileo pointed his telescope in it and he was able to resolve it into individual stars. And he said, that's not some big fuzzy, smudgy blue guys, that's thousands and thousands of fine stars all mashed together, and that's why it looks that way. So that's quite significant advance in the understanding of the Milky Way. Then Thomas Wright came along, he was an English astronomer and mathematician. He then said, I know the Milky Way sort of appears to curve across the sky, but in actual fact, my calculations tell me that it's actually a disc-shaped collection of stars. It's just because of where we are and how we're looking at it, it appears that way, but it's actually a disc shape. Then a Russian philosopher named Immanuel Kant came along, and in 1755 he then said, I agree with you, it's a disc shape, but it's actually a disc full of stars that are rotating round and round. And by the way, guys, you know those little faint smudges up in the sky that we call sort of that nebula? Most likely, I strongly suspect that they are distant galaxies, just like we're living in a galaxy here, and they just turn that point island universes. So they thought, oh, galaxy and Milky Way was the whole universe. So they coined it, that term was coined island universes. So he was the first one who came up with that concept. Then a big name in astronomy came along, Henrietta Leavitt, American astronomer, a lady astronomer. In 1912, she discovered the period luminosity function of Cepheid variables in the Small Magellanic Cloud. Okay, let's stop right there and see this. That's a really, really important thing. So let's talk about the Small Magellanic Cloud. I've got a lot of new members in here, so we're just taking nothing for granted. We're going to talk about variable stars, what that period luminosity function means, and what the relevance to astronomy that it is, namely the inverse square law we're going to be talking about. So the Small Magellanic Cloud, it's a dwarf, there's actually two of them, the small and the large Magellanic Cloud. They're very small dwarf galaxies. They're called irregular, and you're going to find out how to classify galaxies. You're going to know all about this by the end of the night. So it's a dwarf, irregular galaxy. There's a large one and a small one. The satellite galaxy, in other words, they go around the Milky Way. The Milky Way's here, they're just sitting up above the Milky Way, just as a satellite following. They're actually going through the process of merging, or certainly having at least an interaction with the Milky Way at the moment. So when you look up to your sort of southwest part of the sky at night time, particularly in the southern hemisphere, New Zealand, you can't see it from the northern hemisphere, you'd be forgiven for thinking you're just looking up at some wisps of clouds, small amounts of patchy cloud in the sky. And often you point them out to people and go, oh, look, that was cloud. Yeah, fair enough, they do look like cloud. How do you know they're actually going through interactions at the moment? Because this is part of today's lesson, is all about multi-wavelength observation. That's how we see it optically with our own eyes. If you shine a radio telescope at that, and you'll see the hydrogen gas of these two large and small Magellanic clouds is actually merging in with the alpha gas layers of the Milky Way. The process is going underway, and it all comes down to how you look at things. So that's the Small Magellanic Cloud, and the reason she picked on at one place like that, all the stars is important. All the stars are the same distance from one another that she looked at. Now, variable stars. What are variable stars? Stars spend 90% of their lifetime on what they call the main sequence. This, by the way, is called a Hirschsprung-Russell diagram. You can have a look at it. It has brightness or luminosity on one side, a logarithmic scale, and your temperature on this scale here, the logarithmic scale. And you can do some further reading about that if you wish. So that's what a Hirschsprung-Russell diagram is all about. And you'll see this big strip down here. That's called the main sequence. You've got your small stars here, and it goes up. The sun is sitting in there somewhere, and then it's slowly increasing, and the stars go up in size. Now, they spend 90% of their time on the main sequence, which means that's the stage in their life they're busy burning and fusing hydrogen in their inner cores. And as long as they're doing that, they're happy. They're relatively stable in terms of luminosity or brightness. They just look nice and steady, and they're very happy. But all good things like a life must come to an end. They use up all the hydrogen in their core, and they move along the graph out to these regions here called giants and supergiants, and there's even hypergiants up here as well. And what happens is when they stop burning the hydrogen in their core, they then go through a process where they start burning hydrogen and later helium in their outer shells. And when that goes on, those stars become a little bit less stable. But in particular, they're no longer stable with respect to the luminosity. Suddenly you've got this nuclear fusion going on the outer core, they get bright, they expand and they contract, they expand and they contract, and they get into a cycle of doing that, which is quite complicated physics, but they do. They get into a cycle of doing that, and they're naturally called variable stars, because their brightness is going up and down, up and down. And that immediately tells you that star has left the main sequence. It's no longer burning hydrogen. It's in its later few years. It's sort of in the rest home, so the stellar rest home. And it's quietly burning hydrogen and helium and so on in its outer shells. So that's the Hirschsprung-Russell diagram. That's why they pulsate if they start contracting and expanding. Now here's what I put this one on here. This diagram shows you, because not all red giants, but usually most of them do start to pulsate and so on. But in particular, there's a region in this Hirschsprung Hirschsprung-Russell diagram called the instability strip, and that's where your key variable stars are that are of particular interest. They have this period luminosity function whereby they predictably and reliably pulsate. And there's three main groups we're going to be looking at: the Cepheid classics, which is the type 1s, the Cepheid type 2s, also known as W Viginus, and your RR Lyrae variables. And you've probably heard of your Lyrae variables, and they're sort of a bit dimmer and sort of sitting out here somewhere. So that's where on the HR diagram that these guys sit, these variable stars that reliably pulsate in a regular fashion. Now, I thought I'd just take a step back. There are many types of variable stars. It's a whole science. It's a whole field of astronomy. There's two different types. First of all, let's get these ones out of the way. Extrinsic. And that refers to the reason that they appear to be pulsating and varying in intensity is because of geometric factors, not because they're intrinsically going through a contraction and expansion. You've got two stars, and the binary stars, they're going around one another, and they're eclipsing one another in our line of sight. So the light curve goes up, it goes down, and you're looking at 2, then you're looking at 1, and so on and so on. And that's got nothing to do with the stars. It's just more or less like a call it an optical illusion if you want, for the right words, but it's a geometric reason for it. It's called an extrinsic variable. These are the ones that we're concerned about, the intrinsic ones, repeating cycles of just interstellar physical processes post-main sequence, namely burning hydrogen and some helium in their outer cores, causing a regular expansion and contraction. There are many different classes on different parts of the Hirschsprung-Russell diagram, but there's 4 classes in particular that are important to astronomy because they have this period luminosity relationship. So you might say, okay, we know what a variable star is now, we know what a small magellanic cloud is. Hey, but what's all this period luminosity relationship? And that refers to that these, and I've done a nice graph here to show you the type 1 and type 2 Cepheids, is that what Henrietta Leavitt showed is that these guys regularly pulsate, and it's usually in a number of days, sometimes up to months, particularly for these type 1s. And for a given period, in other words, if it's 3 days or 5 days, you can actually calculate how luminous or how bright they are. Their intrinsic brightness, not how they look from here, but how they actually are bright themselves. So, for example, if you had a star that had a regular, every 3 days it went through the same cycle, you go up here to your graph and you say, okay, that's XYZ luminous. If you had another one here that was, say, a week, that took its cycle was a bit longer, it was a week, you bring that up here to the graph, go across, and that might be sort of 100 times or 1,000 times that degree of luminosity. So the longer the period or the frequency, the brighter the star is. And it's got a nice relationship going on there. It's very, very reliable. The other point from this graph is that the type 1 Cepheids, which we're going to come to shortly, are a lot brighter than the type 2s for any given period. In other words, if you see one of them there and it's a, say, 5-day cycle, and then you determine whether it's a type 1 or 2 before you can actually calculate the luminosity. And you can do that quite readily. They are different stars, which we'll talk about shortly, why that is so, how you can actually determine if they're type 1 or 2. But I hope that all makes sense. You look at a variable star, yep, we've got a variable star, we look at its cycle, regularity, and you can work out how bright it actually is. Now, this leads us to the, so you might say, okay, big deal, we know how bright that star is. Well, how does that change my life? So the key to it is, if you know how bright a star actually is, you know it's what they call its absolute luminosity, you know how bright it is from Earth, its apparent luminosity, you stick your eye in the telescope and have a look. So you know it's apparent how it looks from here, you know how bright it actually is. From there you should be able to work out the distance, and that's the key to it all. It's called the inverse square law, whereby as light scatters out from a source, whereby if you double the distance between, say if that's the star, and you double the distance, say from here R to 2R, that star becomes 4 times dimmer, 1 over 2 squared. If you were to 3 times, triple the distance between the star, that star becomes 9 times dimmer, so 3 squared. So it's called the inverse square law. So immediately between the absolute brightness of the star, the apparent brightness, in other words, how it looks like from your telescope on Earth, and the distance between them, all those are 3 tied in together. And if you've got any two of them, you can work out your third. And that's the relevance. These variable stars are really key to working out how far away distances to other galaxies and so on. That's why we're talking about them today during Introduction to Galaxies. And of course, Henrietta Leavitt, the reason she discovered this because she made the quite reasonable assumption, the correct assumption, that all these stars in the Small Magellanic Cloud are all the same distance from us. So she immediately knew the distance factor. She knew what they looked like in the telescope, so she calculated for each one the absolute luminosity, and hello, she started plotting them on a graph. Oh, we've got a pattern here, and that's how she discovered it. So that's a key point in the history of on examining galaxies. Now, Cepheid variables, let's just have a talk about the Cepheid variables. There's two types, as we talked about. Type 1, the classical. Now, population 1, metal rich. So, when you probably heard people talk about population 1, 2, and 3 stars, what's all that about? It's about generations of stars. After the Big Bang, the universe was pretty much just hydrogen and helium and a small splash of lithium. But for our purposes, like hydrogen and helium. So the first stars that formed from hydrogen and helium were just literally that. They had no metals. Metals is a word that astronomers use to describe any element heavier than hydrogen or helium. And by the way, those metals, heavier elements, there's only one source they can come from, and that's nuclear fusion inside a star. So there's no one around the first generation of stars. They were called population 3 stars. They had no hydrogen and helium. They haven't yet been able to identify them. Hopefully the James Webb Space Telescope, when it gets launched in October next year, will start producing that data and seeing them perhaps 2019, 2020. So population 2 stars is the next generation of stars, because that first generation, population 3, they then went supernova, blew up, spewed out all their contents, namely all these metals, now that they've been busy producing through nuclear fusion, into the interstellar medium. The next generation of stars that come along now incorporate those metals in with their hydrogen and helium, and they've got metal on board, but they're still relatively poor in metal compared to the next generation. So the second generation of stars, population 2. Now, population 1 stars is that third generation. Our sun, the current, most of the stars in our vicinity are all third generation stars. With that second generation, they had metals in a relatively poor amount. They then produced more and more metals inside them. They went supernova, they spewed out all their contents with more metals, enriched the interstellar medium with more metals again to create this current generation, call it a generation 3 if you will, of stars, and they're called population 1. And it just so happens the population counts backwards. They go population 1, population 2, metal 4. Population 1 they call metal rich. That's the current like our sun, about 2% of elements other than hydrogen and helium. And then you've got your population 2, and they call those old stars. Population 3, we can't see them here. They don't have any heavier metals in them. So the type 1 Cepheids are population 1 stars, they're metal rich. And when you get, they call it metallicity, how much metal is in a star. And one of the factors that metal does do to stellar astrophysics, it makes a star burn more brightly. So these Cepheid 1 stars, they're burning more brightly. The population 1 metal rich, in other words, sort of call them 3rd generation stars. They're usually bigger stars. They originate from stars about 40 to 20 solar masses, i.e. 4 to 20 times the mass of our sun. Stars are grouped in spectral classes, according to their temperature, surface temperature. And this is just one here for some of the knowledgeable guys in the group, just want to know a little bit more about Cepheid variables. The F6 to K2 are the spectral classes that go on to become type 1 Cepheid variables. And it's usually, they're in the process of becoming yellow giants and supergiants. Their periods are day to months for their cycle. The luminosity, check this out, they can go up to 100,000 luminosities. That means 100,000 brighter than our sun. Our sun's pretty bright, but you imagine that 100,000 times. That's how bright these babies can shine. And immediately that tells you, oh, that means you can see them from a long distance, doesn't it? Exactly, and that's why they're very important for the study of galaxies. And yeah, you can determine the distances to galaxies beyond our little neighbourhood of local galaxies. So galaxies far away, they're very useful for working out distances. Your type 2 Cepheids are your next lot. They're population 2, like the second generation, if you will. They've got some metal in them, but a relatively poor amount of metal compared with, say, our sun. They're smaller. They come from stars that are smaller than our sun. Their periods are usually range from anything from 1 day to 50 days. Their luminosity is a lot less than your type 1s. They've got less metal in them, so they burn less brightly, and you can see the graph they sit down here. For a given period, they're less bright. And they're used to determine distances to globular clusters, which we're going to talk about shortly, galactic centres, and just the local galaxies within the local group cluster. RR Lyrae, so we've talked about Cepheids 1 and 2. These little ones down here are a little bit dimmer, but nevertheless they're very useful variable stars that have a reliable period luminosity function. RR Lyrae variables, and they come from spectral class stars from A through to F. They sit on what we call the horizontal branch, which just refers to a part on the HR diagram, part of their evolution. Their periods are also, like the type 2, is about 1 to 50 days. Their luminosity, once again, is dimmer. This is luminosity here, that's brighter, that's only less dimmer. They're actually a little bit dimmer again. You can use them to determine distances also to the globular clusters, the galactic centre, and just the local bunch of galaxies. And the main message there, there's 3 groups of them there, in particular those type 1s, they burn really, really brightly, and you can use them to measure distances to galaxies, certainly considerable distances away from ours. Another little bit of random humour thrown in there. Just changing chapters. Okay, Houston, we have a problem. So we've gone through history and we're determining distance to some of the galaxies and stuff, but in the meantime, we're still trying to work out our own galaxy. Where do we sit in this galaxy? We've always sat at the centre. You know, the sun goes around us. Hey guys, it doesn't. Oh, okay then. Well, maybe we're at the centre of the galaxy. We didn't know that sort of stuff, so people just assumed, oh, well, everything goes around us. But they had a problem. They couldn't actually find the centre of the galaxy. Why? Dust. Big dust. You're familiar with that site? Those are big, thick lanes of dust, of interstellar dust between the stars, the results of previous big stars that have done that spewing and produced dust and so on. The reason you can't see through dust is a process called extinction, and that is where dust is very good at absorbing and scattering the ultraviolet light from really large, big, hot young stars, and also medium, average-sized stars like our sun that produces light and what we call the optical wavelengths. That's the visual wavelengths that we see, less energetic. So, and that makes up a large population of the stars, your big bright ones and your medium ones, and the dust gets in between us and them, the dust absorbs it and scatters that light and we can't see it. So the appearance appears a lot redder because of the scattering and a lot dimmer. So, what are we going to do about that? We can't see the centre. And that is where a gentleman by the name of Harlow Chaplin rolls up. Come on, Harlow, show you my friend. There he is. So he was an American astronomer. In 1918 rather, he studied distances to 1993 globular clusters away from the Milky Way disk. So what does all that mean? So what globular clusters are these things here. They are just clusters of stars. They're old population 2 metal poor stars. They're really packed in tightly. There's hundreds of thousands of them, tightly gravitationally bound, and they hover out in the halo of galaxies. Now, they are still a little bit of a mystery. There appears to be, I think it's about 158, I think there's even a bit more than that now that I've identified. We can't see a lot on the other side of the galaxy. Possibly it could even be 180, possibly up to 200 of them. That gives you an idea. There's hundreds and hundreds of them, for example, the Andromeda galaxy. All the galaxies are different, but a very common feature in large galaxies. And they sit around in the halo like thus. Here we go. And you'll see here, and that's what he found out, here we are here. So here's the galactic centre and the galactic bulge, which next week, or next month rather, we're going to do a lot of study into all of this in detail. But here's that disk that we're looking through. We can't see through there, but you've got these globular clusters sitting up here, like tower beacons above a rich thick fog. And Harlow Chaplin said, well, why don't I study these and work out the distances to them? So, in globular clusters, one of their features is there's loads of RR Lyrae variable stars in there. And that's because we learned before, they're from population 2 metal core stars they come from. And they're dim, but you can see them within our own galaxy. That's not a problem. So he was very astute. He picked out 93 of them. With the RR variables, he was able to calculate the distances. And from that, he was able to build a bit of a 3D picture of what was going on. And he quite correctly said, look, all these globular clusters are pointing to this sort of region around here. They're all rotating around something, and it makes sense. They're going to be rotating around the centre of the galaxy. And that was a very correct assumption. And from then, they were able to deduce that actually we are 26,000 light years out and in suburbs away from the centre of the galaxy. So that was another big push forward. And how did they do it? Through variable stars. And that's the importance of those variable stars. You can tell distance with things, and you can work out shapes and geometrics and so on. Then along came, here's the big giant tonight, the big giant of astronomy, Edwin Hubble, American astronomer, and yes, quite fittingly, quite rightly so, the Hubble Space Telescope was named in his honour. And he made 3 remarkable discoveries, which we're going to have a look at. Cepheid Variables and Andromeda. He developed the Hubble classification system of galaxies, which is still used today, and very important law used in astronomy and cosmology called Hubble's law. So let's have a look what he did. So first of all, okay, so he found Cepheid Variables and Andromeda, big deal. The relevance of that is that up till then, remember they just saw these little smudgy things in the sky. They didn't have a big, powerful telescope necessarily, and they were just called spiral nebulae. They didn't know much about it. Immanuel Kant, remember, he sort of has a bit of a philosophical sort of question. So by the way, I reckon they're probably island universes, different galaxies. But it was just that. It was just a philosophical thought. So Edwin Hubble got his new, it was Mount Wilson, his telescope. It was a big new one at the time. He looked closer at this and sort of in the Andromeda region, this fuzzy, and he picked up and identified some Cepheid variables in there in that galaxy. So he naturally went ahead and did the right thing, measured the distances, and that came out to 2.5 million light years away. Whoa! You know, a light year is 10 million kilometres, the distance that light travels in a year. You're talking 2.5 million kilometres. That's a long way away. So if something is that far away and it's that big in the sky, holy moly, that must be huge. And clearly, it was pretty obvious. Hey, that was a galaxy. In fact, that's bigger than the Milky Way. So that was evidence and proof that yes, the Milky Way is just one of many galaxies. There's nothing special where we sit in the Milky Way, and there's nothing special about our galaxy, the Milky Way. Sorry, guys, to blow you, drunk tonight, but we're not special. So the second thing that he did, he introduced a classification system. The more he looked at galaxies, embraced the concept of galaxies. He looked and looked and looked at galaxies, and he found a large number. You could actually start to classify them by how they looked in optical wavelengths, just through a plain telescope and visible wavelengths. And he said, look, it appears to me that there's 3 main groups. That there's exceptions to it, but there's galaxies that I'm going to call ellipticals, the sort of ovoid, spheroid sort of shapes, some a bit rounder than others. And there's a spiral group. Most of them are either ellipsoid or spiral. There's also another group in there which look very, very similar but aren't quite these two either. They call theirs lenticular. So he came up with this way of describing ellipticals as such, spirals, he just called them all spirals at this stage. And lenticular, the word lenticular means lens shape. And these ones here didn't have the spiral arms that he saw, but were still a nice disc. These things weren't discs. These were sort of more 3D spherical, like it. And they got stretched out to, say, the shape of a football, a rugby ball, for example. These guys were disc shaped. Some of them had little spiral arms. This one had a disc shape here, but it had no spiral arms. It was sort of an intermediate. So he called those lenticular. And that was his initial Hubble's classification scheme. They call it a tuning fork. You might hear that being mentioned, and so it looks like a tuning fork. Then, naturally, things get more and more refined. He then sort of started, this is still Hubble's work, he broke down the elliptical galaxies actually out to E7, as per the last diagram. So he called the really pure round spherical ones E0, and then as they got more and more stretched out, elongated, he called them E7. And you match the picture up with what galaxy you happen to be looking at, and you name it an E0 right through to an E7. He also did a similar classification system to the spirals. The other thing he noted was that he said, look, some of these spirals actually appear to have bars in them as well. So he called these ones spirals, and he broke them into barred spirals. The other thing he said, look, there's also varying degrees at how big your nucleus is in the middle and how much these arms are spread out or tightly wound in. And he labelled these A, B, and C. So your spirals he labelled S, all S's. He then broke those down to subdivisions A, B, or C, depending on how loosely or tightly your spiral arms are and how prominent your nucleus is. And he did the same with the bars too, and he labelled those SB, so SB, A, B, and C. Make note of that, guys, because you will be quizzed on this later on. And the lenticular ones, he called it, the 0 stands for if they don't have spiral arms. So S0 and SB0 for a barred galaxy, it's disk, but it has no spiral arms. So that was his further one. Then a guy by the name of Gerard de Valkalua came along, and he refined it even further. He said, yeah, I get all that, but hey, there's also another group in here. I'm struggling to find out whether they got actually bars or no bars. So he called these galaxies intermediate spirals, and also kept the system going A, B, C. He added some other systems in there, D and M, which aren't used so often. It's predominantly the A, B, and C that's used. He also added in two other groups, irregular galaxies. Notice how these galaxies have all got some sort of symmetry going on. The other thing you'll notice here is notice the ellipticals are brightest in the middle and then slowly fade out, as opposed to these ones here, the light is distributed throughout the whole galaxy. That's another relevant thing. So he said some galaxies, there's no pattern to the light, there's no real symmetry or regularity going on. He called them irregular galaxies. He also added another name in here called peculiar galaxies. Galaxies that had some sort of unusual feature about them of interest. So that's sort of pretty much the classification that's still used today for optical observations, that is. So let's summarise that. Based on morphological appearances, you've got your ellipticals, which make up greater than 60% of galaxies, your spirals and your barred spirals, and any intermediate spirals that make up just under 30%. Combined, they make up 90% of galaxies. You've got some lenticular guys in here that have a disk with no spiral arms. You've got your irregular ones with no sort of symmetry to them. They're less than 15%. There's not so many of these. These are the big group that more than likely when you meet a galaxy up there, it's going to fit one of these two. They've also they've got galaxies they're called dwarf galaxies, which refers to very small galaxies. Classical example is your large and small Magellan clouds. And yes, I thought you just said they were dwarf galaxies or irregular galaxies. Make up your mind. The answer is you can have a dwarf irregular galaxy, you can have a dwarf elliptical galaxy, and so on, a giant elliptical galaxy. So they call a small galaxy, they call it a dwarf galaxy. You can have a dwarf irregular, a dwarf elliptical, for example. And those are the common ones, actually. And there's the peculiar ones. You think, what the going on there? Jeepers. And that's usually a presence of some sort of unusual sort of feature going on in there, which will come to it, usually involves some sort of merging or interactive process with another galaxy. So that's the morphological, that's the main way. You'll also see other little ways that galaxies are labelled. I'll just throw them in here, don't want to tie you down, but it's just so you think, oh, okay, can you read it? Yeah, I was told about that. You could label galaxies to what sort of activities going on. All major big galaxies have in it, right at their heart, a supermassive black hole. Millions, if not billions, of solar masses. Most of them, particularly ones around here, including our Milky Way one, they're quiescent. They're lying pretty quiet. They're not doing a heck of a lot. They're sitting there quietly. You get particularly the older ones when you look further back through the observable universe. They're supermassive black holes that are chewing and spewing. They are busy churning away material and spewing it out. They call those AGNs, active galactic nuclei. So they call those active galactic galaxies, and these ones up the Milky Way, normal galaxies. So if you see a galaxy beside it, that's all that's referring to. We talked about usually peculiar galaxies, some sort of dynamic process that's going on. And particularly when galaxies merge, there's different types of mergers. When there's a wet merger with a lot of gas and dust merging, you get exceptional, really unusual amounts, high amounts of star formation rate. And they call those starburst galaxies. So that's what all that is. It's usually a peculiar galaxy. Don't get bogged down with that. It's usually a peculiar galaxy that's going through a merger process with just a whole lot of unusual amounts of star formation. So, when you meet a galaxy, what sort of galaxy is that? There's four major questions you've got to ask yourself. Is there overall regularity or symmetry? Yes, that it's usually elliptical or a spiral or lenticular. If it's no, then it's irregular, simple as that. Is the light concentrated in the centre? Yes, it's an elliptical galaxy. No, if it's spread out, it's usually a lenticular or a spiral, or a spiral bar spiral. Is there a disk? Yes, in which case it's usually a lenticular or a spiral bar spiral. Are there any spiral arms? No, then it's lenticular. Yes, then it's a spiral galaxy or bar spiral. Okay, and then yes, you can take it down further and for further subclasses and so on. But those are the four major questions you ask yourself when you come across a picture of a galaxy in a book or something like that. It's really neat actually, you get a book from the Hubble or whatever, and you look at galaxies and have a go at guessing what sort of class it is, and then go to Google and look it up and see if you got it right, if you didn't find out why. It's quite a fun thing to do. Quite for nerds like me it is anyway. So let's go a little bit more depth. Elliptical galaxies here they make up over 60%. They're ellipsoid in shape, which means sort of oval, stretched out towards like rugby balls. Their brightness is maximal in the centre, and then they fan out. Usually featureless, very smooth, featureless. Their shape range, as mentioned, is spherical, which is an E0, right through they flatten out, called an E7. They have a huge, massive range. They could be yay big, or they could be yay big, like a dwarf elliptical or a giant elliptical. Usually the giant ellipticals sit in the centre of clusters. They're often called CD galaxies. Okay, the stars, once again you know all the stuff now, you know what a population 2 star is. It's an old metal poor star. They usually have a redder tone hue to them because they're off the main sequence and they're no longer burning, and their spectral class can often change. Now, you're probably familiar with the rotating disk, like the Milky Way. All the stars, that's the disk there. They're going zoom, zoom, zoom around the little star. They're spinning in a nice orderly orbit within that disk. Within elliptical galaxies, whole different things going on. It's just sheer random orbits. You've got the centre of the galaxy here, and they're like a swarm of bees, swarm of stars. You know, my star might be going this way, then coming back this way, another star shooting this way, coming back that way. So if you imagine millions of stars in a big, massive, random swarm, every star is just heading in an orbit around, very highly elliptical orbit, around the centre of the galaxy, comes out here, interacts with another one, heads back that way, another star here going that way, and so on and so on and so on. So just random orbits around the centre, and a swarm is probably the best way of describing, and that's why it's just featureless, very smooth. There's not a lot of interstellar medium gas and dust going on there. Very little star formation going on in these elliptical galaxies. They do tend to dominate regions of higher density within galaxy clusters, and that's a very important factor. We'll go into more. One of the sessions will be on how galaxies form and evolve, and that's very, very relevant. Elliptical galaxies love to be in the city. They love density. They're in regions. They hang out in regions of high density, and there's a reason behind that. Spiral and bar galaxies. Once again, we're going to learn a lot more of these in session 2 and 3. We live in one, of course. We've got a flat disk. The light is more evenly distributed. There's a structure of spiral arms. We're going to talk a lot about that. We're going to learn about the spiral arms and what makes those arms function. The size range is very narrow, so you don't have big ones, you don't have little ones. They're sort of yay big, and there's very little variation. Very rich in gas and dust, so there's a lot of regions of active star formation, which have a look through your telescope, and you see loads of them: Orion Nebula, and Eagle Nebula, and Swan Nebula, and so on. Now, so let's have some fun here. Can anyone tell me what sort of galaxy that is? Sub-spiral. Yep. And A, B, or C? Would you put that? C. I'd say it's a little bit of tightness there. That's an SA. They consider that reasonably tight, and it's got a reasonably sized bulge there as well. Okay. How about this galaxy here? What would you call that?
SB.
Yeah, an SB is a bar spiral. Yeah, there's a spiral, it's SB. And how about those arms? What do you say about those arms? Would it be a tight A, a medium B, or a loose, hanging loose C? Yeah, it's a medium, it's a B. And incidentally, our Milky Way is thought to be an SBB. I think that someone's called an SB, possibly B/C galaxy. So that's what we would look like. And how about this one then? Yeah, so it's an SB, it's got a bar to the middle, and so the next thing is you think of, okay, how tight or not tight are these spiral arms hanging out here? They're pretty loose, aren't they? They're not tightly wound. So that's an SBC. So, you've got it already. Great. How about this one here? And Greg's not allowed to answer this one because this is a photograph that Greg himself took of I almost looked up there, of NGC 253, the Sculptor Galaxy. Any ideas? So, okay. Well, yeah, it's interesting. It's not really easy to tell. It's not elliptical. And you think, is there spiral arms? It's lens shaped, but I can't really make any spiral arms. It's certainly a disc. Is it possibly a lenticular? No, and that's actually, they decided they can see arms. It's not always easy. There's that I think someone did say they could see some spiral arms. It's not easy to tell. They can't even determine it's got a bar or a non-bar, so they've called that an intermediate galaxy. They don't know whether it's got a bar or not, and it's not easy to tell. And even spiral arms, I struggle sometimes to see them, but obviously the people who know have decided, yep, there's arms in there. And this one here, and that's a classical example of a lenticular. You've got your disc shape, but you've got actually it's no great. You've got no spiral arms going on there. And it doesn't have the reddish hue that you tend to get with the elliptical ones of old population 2 metal core stars. Okay, so lenticular galaxies, they've got the bulbs, the flat disc, but no spiral arms. The lens shape, and that's what the lenticular word means. The light is more evenly distributed, narrow range like the spiral ones. Little gas going on there. They don't have spiral arms. They've got little gas and dust and little star formation that's going on. So they're almost an intermediate, aren't they, between spiral and elliptical. And then you have irregular galaxies, and there's your small Magellanic cloud being photobombed by 47 Tucanae. It's a globular cluster. It's just out there in the constellation Tucanae out to the southwest. It's got a diameter of about 15,000 light years. It's got about 100 million stars, and it's about 210,000 light years away from us. So you're unable to assign them to anything. There's no regularity, no symmetry to that going on at all. So it's called an irregular galaxy. And because it's small, it's an irregular dwarf galaxy. And also you can pin the word satellite in there as well, because it evolves or it quietly moves around the Milky Way. That's another irregular galaxy. No formal shape to it as such, no symmetry. So peculiar galaxies we talked about briefly, presence of unusual features, and usually it means that there's some sort of intergalactic merging or interactive process going on. There's interesting enough, there's a whole atlas of peculiar galaxies where the particular astronomers gathered 338 of them that all show nice examples of different types of peculiar galaxies. You just go and Google that, look it up and have a look through. It's quite an interesting bit of a browse. You can't sleep until the morning, assuming there's cloud cover and you can't use a telescope. A classical example is going to be the Antennae galaxies, which you may not know. Oh, what are they? I'm going to put them on a minute. Oh, you've all seen pictures of the Antennae galaxy. Hode's rings. It's a ring galaxy. They're peculiar, usually from galactic mergers. Really interesting. Our movie lecture is going to sort of in particular focus on that. And there's the Antennae galaxy. And it's two galaxies that are interacting and merging together, and look at all that star formation. So it's no surprise they're also called the starburst galaxy. Remember we talked about, you'll sometimes see the name starburst galaxy, and it's called a wet merger where you have a lot of gas and dust coming together, the pressure goes up and they naturally start forming into stars. Just love that picture. That's a classic picture. Here's another one. Here is two interacting. That was merging galaxies. Merging galaxies, and here this is interacting, not yet merging, they probably will merge, but they're just interacting. There's two key words you use, bridging and tail. See a little tail here, there's the bridging going on. I suspect this is in optical wavelengths, but if you slap or look at that with radio telescope, you see all the hydrogen, you see them linking together more. And that's the sort of image you actually see when you look at the large and small Magellanic Cloud of the Milky Way in radio. You actually see nice little streamers and bridging and tails going on. They are actually interacting. And that's a lovely sort of picture of what they call a peculiar galaxy. Further little comments. It's so tempting to say, is there an evolutionary sequence? There is no evolutionary sequence. They don't just quietly plod along in that direction or that direction. You sometimes can see a galaxy that seems to be moving into another type of galaxy, but there's no evidence to say there's a complete evolution along the line. The Hubble class, we're going to learn more about this later on with galactic evolution. The Hubble class of galaxies really determined by the environment which they're formed. As mentioned, crowded environments, like deep in the inner parts of a galactic cluster, you're more likely to see elliptical and lenticular galaxies. Out in the field, called field galaxies, where it's more isolated in the peripheries of a galaxy cluster, you're more likely to see a spiral, a bar spiral, an intermediate spiral, and so on. So that's just some little further comments there. Hubble's law, so he was a busy man. So he found the Andromeda galaxy was a separate galaxy. He formed a classification system. He also discovered when he was examining clusters, galaxies rather, these galaxies were all receding away from us. He did spectroscopy. He did through the Doppler effect, called redshifting. You've probably heard of that. He discovered that all these galaxies are moving away from us. Oh, that's interesting. But he also picked up that the further galaxies away from us, the faster they are receding from us. For example, if a galaxy, say, 1 megaparsec away from us is travelling away at 500 kilometres per second, get a galaxy, say, 10 megaparsecs might be travelling away from us at 1,000 kilometres per second. So he plotted all that and he created what's called Hubble's law, which is the velocity of a galaxy equals the Hubble's constant, which is essentially the cosmological constant. You might have heard of Landau, or a cosmological constant. That's dark energy, that's the rate at which the universe is expanding, times the distance. And of course, they can get the distance quite happily through variable stars and other methods as well, type 1a supernova and so on. Hubble's constant, the rate of expansion, they're narrowing that down. I think last year I heard it was 68 or something, but I saw an article 2 weeks ago that some data's come out that they've suggested by different measures at 71.9, and they said that's, they did describe their method. It was a completely different method. Like all of them, they say, hey, our method's better than the other. So the bottom line is it's somewhere between 68 and 72. They're narrowing it down, and that's kilometres per second per megaparsec, how fast the universe is expanding. And that was Hubble in those early days, picked up on that law. It's a very, very important law. Busy, clever man. But humour. You can tell I got an iPhone, not a Galaxy. Yeah, we'll move along for time. Tools of modern astronomy. And the bottom one is here, and multi-wavelength observations. And this is all tied in. I just want to go briefly over this. We've learned the importance of observing at different wavelengths. When you go telescope on the ground looking upwards, you've got to go through the atmosphere. The atmosphere's a bugger. It can do two things. One is it's got a lot of turbulence going on. So that the light waves that are coming through are constantly being diffracted in all different directions randomly, and that's what causes your blurring and twinkling of stars. It's not very nice. They can counter that to a degree with adaptive optics on modern telescopes, but still it's a problem. The other thing is the atmosphere itself, the air particles are great at absorbing a lot of wavelengths. They absorb your gamma rays, your X-rays, ultraviolet. They allow optical wavelengths through, which is good, and they block most infrared wavelengths coming through. So the only way around that, put your telescope up in space. And indeed, there are numerous telescopes here. The infrared region, the Spitz is still going, and literally a lot of its coolers run out, and some of the sensors are still working. Herschel's done its job. James Webb we talked about. Next year, next October, it's due to be launched. Hubble, after, of course, Edwin Hubble, which we all know about, that actually sees some near infrared, that's what NIR stands for, through the optic and actually right through the near ultraviolet, almost to some of the early extreme ultraviolet wavelengths. So that's been magnificent. You've got the X-ray telescopes, Chandra, NuStar, XMM, Newton, gamma ray, of course we talk about gamma ray bursts and so on. There's gamma ray detectors in space, but the only way you can't reach them on Earth. And this is the importance of multi-wave observation. The key point here, many objects have stacks of different physical, astrophysical processes going on inside them. And they all emit electromagnetic radiation, light, in different wavelengths. To get the full picture when you see an object, really what's going on there, you've got to individually pull it apart and look at different wavelengths. And here, for example, is looking at the Whirlpool Galaxy in visible light, and you see pretty much that's all the medium-sized stars giving out light and optical wavelengths that we see best in, and that's the sort of picture you see. Remember your big hot OB stars that we talked about, they give out ultraviolet light, and if you look at a galaxy, say with the Hubble and ultraviolet light, that's the sort of picture you're going to see, and that's telling you where all the big hot OB stars are placed. A lot of your cooler stars, your more red light stars, they give out cooler light and infrared. So you put your infrared telescope, point it that direction, and that's the sort of picture, and that tells you where the stars, the cooler, older, redder stars are orientated. You point your radio telescope at the Whirlpool Galaxy, the same galaxy, but look, you're getting a completely different picture. You've got a bit of a tail going on there too, some sort of interaction. But you can see the pattern of where all the cool gas, in particular the hydrogen molecules are. And then you go to X-rays, and you see like the centre of the galaxy, there's a bit of X-ray activity going on. What's all this stuff here? Usually hot gas. Most galaxies have patches of hot gas, certain clusters do too. Supernova remnants have hot gas. So they're common sources of X-ray, but often at the centre of galaxies, you've got those supermassive black holes. There's activity going on there. So that's really the point between that little take-home message, tools of modern astronomy. You've got to get above the atmosphere to really have decent looks at objects in all wavelengths to get the full picture of what's going on. That's pretty much what we've talked about before we move on to our movie. The movie's a bit more passive, so we've met some interesting people. We've talked about some principles with the variable stars, Cephids and RR, crucial for measuring distances. We know how to classify galaxies now. While we're talking about Hubble, we talk about the very important Hubble law for measuring, once again, another way to measure distances to galaxies. It's another method. And we've learned the importance of putting telescopes up in space to get above the atmosphere and have a decent look at something in different wavelengths. So now we'd like to move on to this lecture. It's a lecture on Hubble's galaxy. So it's given by Professor Meyer. Bangs on 30 minutes there, and then we're out of here. And it's just relevant. He'll go over a lot of the stuff we've talked about, but he just adds a different dimension to things, and he'll talk about other little things that it's matched the talk quite nicely. I know I've rattled on for a while, a bit longer than I thought, but any questions or anything? Any of that? That's good. Oh, yeah.
The galaxies which Hubble has classified is based on optical, so it is what we see.
Yeah, it's based on
actually it may be different.
Yeah, absolutely, and that's why there are other classifications like normal and active galaxies and so on. So it's based